Okay, so I was glad to be here with Tia tonight, and we have, sure, a very nice discussion. Looking forward to it. So let me start with some introductory part of the topic. Well, as you know, I'm sure you know, being here in this audience, coming to this event, that so far there is no cure for Alzheimer's disease. No cure. The cure means you cannot stop the disease, you cannot revert the disease. It's still a progressing disease and a threat to people that are having the disease, and it's a deadly disease. There is some treatments that are suggested many decades now already, and but these treatments are only managing symptoms or sort of perhaps slowing down the progression to a minor extent, but these options are really individually to be applied depending on the patient and its background. So this is sort of the starting point. And when you look at Alzheimer's as a disease, there is individual risk factors for the disease, and so every individual has particular genetics behind it, has risk factors, risk genes, like vascular problems, perhaps, or even other psychiatric conditions that sort of, you know, provide the background for a threat to get this disease. Traumatic brain injuries also, or alcohol use is of course also a risk factor. So Alzheimer's has been worked on for over 100 years now, and interestingly enough, when I worked on the book, I started with the very history, and I would even go that far that Alzheimer's disease research started even before Alzheimer was working on it, because this condition was already known before Alzheimer's described it in his first writings. But so there is display of this disease research over the last 100 years, and this is all the exciting experimental and medical progress that has been made. And my own little contribution in the beginning of the 90s, while working in the States actually, was here in the 1990s early on. So in the 1990s, when you read the book, I think you realize this very quickly, it was really the hot phase of Alzheimer's research in a way. And looking back now with what we have on new possibilities of therapies, we are still stuck a little bit in the thinking of the 90s, which is, as I think, a real problem. That's why I would plead for this paradigm shift, and I will talk about this more in a minute. So this history is interesting because it also tells you, strategies and conditions that we realize also in today's research world, like competitive activities. So these are pictures of Alzheimer and his mentor, Emil Kappelin was the first psychiatry specialist who believed that every psychiatric disorder has a biological basis. So he went away from Freud and other ideas, and therefore the findings of Alzheimer's, when looking through the microscope of Alzheimer patients, it really played in his cards, because he could say, well, there is a new disease, but it has a biological background. So this is the reason, one of the reasons, the historians told me that's one of the key reasons why Kraepelin was so hot to really introduce this new label of the disease, Alzheimer's disease. I have to say that Alzheimer never got any payment from Kraepelin, or he was sort of a freelancing researcher, and Kraepelin also sort of wanted to give him some, special treatment by labeling this disease. He supposedly first described after his name. In in the discussion of who was first in looking at this kind of disease, one has to mention also Oskar Fischer and his mentor Arnold Pick. Some of you may know Pick's disease, which is also a neurodegenerative disorder, and Oskar Fischer and Alois Alzheimer, they basically found the same thing, but for very tragic reasons, Oskar Fischer never got that much acknowledgement for his findings. So, to be exact, it should be more Alzheimer's Fischer disease, but rather not only Alzheimer's disease. Then in the 80s, biochemistry started to gain more attention and more methods and technologies. George Klenner described the amino acid sequence of the peptide that is found in the plaques in the brain, and these plaques were described, as you may know, by Alzheimer's, dense core material that you find in the brain. And Colin Masters and Conrad Baywater, they finished up the sequence of the amyloid beta peptide. That's the name of this peptide. And the other major hallmark of the tissue affected by Alzheimer's disease is the tau protein, so tangle, fibrils that are building up in nerve cells. This is also described, was also described in the 80s and 90s in more detail. Now, after describing the amino acid sequence, the race was on for the cloning of the gene of APP, the precursor protein of amyloid protein. So today, this is just a quick overview of all the drugs and compounds that are clinically testing to treat Alzheimer's disease. And there is currently 126 compounds in clinical trials, and 28 in phase 3, 74 in phase 2, and 24 in phase 1. It's changing these numbers as we speak. But just to mention that they have different targets, basically, but the main target, or the most prominent and most promoted target, is still the amyloid beta protein that is found in the plaques of the brain. And I would like to describe why this is the case, because this has great implications for treatment. Now, there's different hypotheses of the disease, obviously, and there's one hypothesis that overrules all other hypotheses, which is the amyloid hypothesis or amyloid cascade hypothesis, which has been formulated in 1992. I'll go into detail in a minute. So this tells you that most of the drugs that are tested are based on this thinking. There is a peptide deposited in the brain of patients, and we have to get rid of this peptide, and we have to prevent its generation. That's the basic idea. In 1992, there was the first description of this hypothesis by Hardy and Higgins, and this paper is one of the hallmark papers of Alzheimer's research. It's still cited these days, and it was very important, but important in many ways, because it also set the pace for the research of the next decades. It's now 30 years old, and there has been several reappraisals of this hypothesis, and minor modifications, but still the key message is there is this peptide that is built, it's depositing, and it's inducing different detrimental stages, detrimental processes leading to nerve cell death and dementia. So again, there is a cause and effect relationship proposed. Amyloid is there, and then later on dementia is introduced. So if you look through the literature, and I did that very extensively, you realize that for 30 years, all research around in Alzheimer's disease, basic clinical research, was highly centric on and focused on amyloid beta peptide. Whatever was found in experiments was always put into the relation of amyloid. We may discuss later why this is the case, but it's the fact. So it's this hypothesis that dominated all other views that were coming up. Every new idea that was presented, excellent papers, excellent work, was always thought of, well, how could it relate to amyloid beta? So from the very beginning, the problem, and I would even say the mistake in the field, was to define Alzheimer's disease just as a plaque and tangle disease, or plaque and tangle. This is the definition, but I don't think that it's really the case. I don't think that's really a good idea to think as such. So the amyloid hypothesis is the basis of so many trials and so many approaches, and this is some biochemistry, but to just tell you that fantastic molecular biology experiments and fantastic biochemistry has defined the exact biochemical process, how this peptide that is deposited in the brain as a plaque is built up, how it is forming oligomers and monomers, the whole biochemistry. And the field believes that by interrupting the production or its fibrillar formation or removing it when it's already deposited, this might be a way to treat Alzheimer's disease and to improve the cognition. But in the last 30 years, most of these drugs that have been targeting these pathways, they failed. There were hundreds of drugs tested and hundreds of failures, and for some reason, and this I'm pointing out in the book extensively, there was always the expectation, well, the next trial will be, so let's just wait and hope. The next one, you have to treat earlier, you have to treat differently. There was always excuses, but no one really questioned this hypothesis in its core. Now recently you may have heard that end of last year, an antibody that clears off amyloid, or induces the clearance of amyloid out of the brain, called lecanemab, was published, clinical data was published with some minor effects on the cognition. And only a few days ago, donanemab, the second antibody, anti-amyloid antibody, was introduced, supposedly doing the same thing. These studies, these clinical studies, are published in fantastic journals, and just to focus on these two antibodies. Now this is, for example, one original picture out of this paper showing the lecanemab, an antibody that binds to certain types of the amyloid protein in the brain. So the patients get infusions every other week for as antibody infusions, and then they are tested month by month on the different scales of memory and cognition. And so you see, when a patient that is receiving placebo is going down in his cognition in 18 months, and then you see an improvement with lecanemab. This improvement is mathematically, statistically calculated as being significant, but clinicians tell you can't even realize this. Many clinicians that this minor effect you can't realize. On the other hand, this antibody perfectly clears the brain from the plaque. So the plaque is gone, the amyloid is gone, but the cognition is not coming back, or the decline is not really stopped. It's just a minor effect. So this is the hype in the field that started end of last year. And now, in the last couple of weeks, there was a second antibody, and we may discuss later the pros and cons of these antibodies, but it had a similar turnout. Still no cure, still no reversal, still no stop of the disease, a minor, moderate, less decline in cognition. What I also want to stress here is that for those that you're interested in this, placebo means an infusion of saline. It's just salt or water solution, so to say. So you're comparing a saline solution with an infusion of an antibody, which is, if you would propose this to the ethics committee of mouse, for a mouse experiment, everyone would say, well, we can't do that. You need a proper control. But here in the human trial, that's obviously what is done, and this may also explain some of these differences. Anyway, so there is a long list of debates and papers arguing against all this data, this new data that are hyped so much, and so it's all published in very prominent journals, and obviously there is a need for other measures in Alzheimer's. There is even a discussion going on saying, well, these new drugs, they have tiny benefits, they have huge side effects, they have a high price, very, very expensive, and not that much people are really eligible for being treated with these antibodies. So you have to, have certain conditions, or low blood thinning substances. You cannot give these antibodies with blood thinnings and other conditions. So it's a high rate of side effects and high selective selection of the patients. So these people here from this review, they say, well, let's just stop it now and let's think differently, and that's basically also the message what I wanna put forward. And there's no lack of alternative hypotheses. So it's not like amyloid hypothesis is the only thing that has been found and suggested. There is quite a number of different hypotheses that have been ongoing and proposed right from the beginning. And but you realize when reading this work, and when you are part of this community for some time, that there is this main dominating hypothesis, and whatever comes up will not be followed. There is the mainstream, and it's really hard to bring through the message of alternative views. And so it's hard to argue against the mainstream. So these are certain hypotheses that are all substantiated with great data, and now more recently people come back to these hypotheses for reasons I will point out in a minute. And so there are alternatives. There is already in the 1990s, there was proposed that this is the disease, a disease of the transport in the nerve cell. And all these different risk factors and proteins associated with the disease are linked to this network. So it's not amyloid on the top, it's just a transport problem in the neuron. All valid data, fantastic work, but no one really realized that this is of importance. There is an alternative amyloid hypothesis saying that A-beta might be even a protective protein against oxidations coming up. There is a big issue on the amyloid beta peptide being a protective antimicrobial protection molecule. Whenever you have a microbe or an infection in your brain, amyloid is increased in the expression and binds to these microbes, for example, Candida and other microbes and infectious agents. There is a lot of data showing that whatever infection is going on, herpes virus has been associated with dementia in fantastic papers. But all this information, started also in the 90s. They were all overruled by this dominating hypothesis, which is interesting in itself, but it's also tragic because now, 30 years later, we stand here with watching anti-amyloid clinical trials and seeing these minor effects. So this is all pointed out in the book, and this is much too many words to read all of them, but I just want to stress that in the book I start from the very, very early days and propose and present the different drugs that have been introduced, also the acetylcholine, esterase inhibitors, you may have heard, and so forth, and elucidate why this amyloid cascade hypothesis is so dominant. Now, a picture I took from the sky at night in short exposure, and a picture same place with a long exposure. You may wonder what's going on now. Well, it's just sometimes you have to look more closely and for a longer time be more critical, and you see much more what is actually going on. So, and this will be my final slides, there is a lot of things going on. So in the last 30 years, it has been shown that all these genes named here, they are risk genes for the disease. So individually, if you carry one of these genes in certain, flavor, so to say, then you are at risk. The risk gene is just increasing the risk. It's not determining you for the disease. But you may acknowledge that these are really dozens of genes showing that the disease is age-related and it's a multifactorial, multigenetic disease. And the focus on this, proteins or these genes from the 90s exclusively was perhaps not the best idea. And summing up now all of what I have read over the last 2 years and ideas, of course I made my mind up for something like an own hypothesis, or another view how things may work. So this picture I made in the San Francisco Museum of Modern Art last winter when I visited San Francisco, and it's an artwork from actually a German artist, and that's a sail, a gaze, a cloth that is hanging in the room, and it's sort of changing its condition by a ventilator here and a fan here down. So you could observe how this thing is moving. This reminded me of the brain, because the brain is constantly changing its connections, and so while we are sitting here, our brain is changing a lot. A lot of synapses are built and are cleared, new connections are built, and so forth. But the brain, a healthy brain, can react to all of these changes and the different conditions, and it's highly adaptable and it's highly plastic. So what I figure is that under healthy conditions, you have indeed this matrix that is changing and can adapt. And over time, over the years, of course, you have, during lifetime events, brain trauma, metabolic diseases, and so forth. And this changes the flexibility, which is normal over time. And of course, there are plaques and tangles. More than 30% of aged people have high amounts of amyloid protein in the brain, and no cognitive impairment. And almost everyone at a certain age has tangles in the brain. I was talking to anatomists looking at thousands of brains, and he said almost I never see the brain of an aged person without any tangle. So once you have a risk gene, such as the ApoE4 gene, this condition changes, and the adaptability, the plasticity is changing right from the beginning. The matrix gets stiffer and less functional. And this is under normal conditions with late onset typical. It's similar, but at a later onset. You have your lifetime events. You're starting with a certain genetic setup. This determines what's happening during aging. Finally, and this will be my last slide, I would plea for a more individualization and personalization of the disease. And depending on the risk factors you have, you can define your risk genes. You have preventive measures, nutrition, lifestyle measures, and so forth. And I do not expect that you can treat such a complex brain disease with targeting one protein, which may have only a side effect or side function. That's the challenge, and that's sort of the argument that I'm making in the book. And looking forward to our discussion. Thank you for your attention. I want to remind you that in September is the World Alzheimer's Month. This is just coincidence that we are meeting in September. And next, the other weeks, September 21st is the World Alzheimer's Day. That's it, my presentation. Looking forward for the discussion.
So, just on a personal note, when I was asked to moderate the discussion, I know that Professor Behl had not read my book, Dementia Reimagined, which is not an academic book. It's for the general educated public. Do you have a question? You're having trouble hearing?
Yeah, can you speak closer?
Yeah, I always do that. He had not read my book, and I had not read his book because it's going to come out yet. And they are really sympathetic in their approach to how should we look at this history and what can it tell us about why, for this very common, quite devastating, ultimately fatal illness, have we not made better progress towards prevention and treatment? And many early people are working on this. So how is it that there has been such great progress in cancer, all different forms of cancer, heart disease, stroke, all kinds of things, but Alzheimer's disease and dementia still lags behind. There has not been this sort of big bonus. So I was very, very excited, very pleased to read Professor Behl's book on this session. So one of the parts of the book I most enjoyed is the discussion of cognitive bias. It really goes to this question of why are we still doing this? So a lot of people, Dan Kahneman won the Nobel Prize for coming up with behavior economics, is one of the main authors of the concept of cognitive schemas that sort of help us make decisions, but sometimes do it badly. They sometimes trick us and get us in our direction. So how does that apply in Alzheimer's research? What are your thoughts on that?
Well, this is, there's a lot of bias in this work, in the Alzheimer's community. And I have to extend this, I would say it's many, it's not restricted or to Alzheimer's disease. You have to figure when you are working on a scientific problem, especially of such an impact, that so many people, there's a lot of competition, and that there are mainstream hypotheses, and it's easier to follow the mainstream, it's easier to publish, it's easier to raise money for your research. You follow a mainstream rather than if you bring in a complete new idea. So disruptive ideas which may change the world are hard to get through. And I think this is part of the problem when you, in particular if you're a young researcher, of course you have your academic mentor. If he's an elder person, he will say, well, that's the thing you should work on, and we need grants, and we need money, and there's, as I pointed out in the book, many people start with new ideas, but they didn't come through. And because they didn't get funding. So I think following the mainstream is important. I call it, especially for younger researchers that try to enter the field, there might be something like, it's a little bit nasty, an amyloid firewall for new ideas. And you have to overcome this firewall, and this is hard. And so you follow the mainstream, get an easier life in science, in communication, in positions, in grant money. This might be part of the problem. The other part, yes, the data that you are showing that amyloid is in the brain, the biochemistry behind it, there are fantastic papers, there's fantastic experiments and experimental data. And in the 90s, the golden years of Alzheimer's research, when Alzheimer's was mainly amyloid research, pieces fit together and were put together just as a puzzle. They just fit. There was the genetics, there was the mouse models, this and that, and everyone was happy, it all fits together, forgetting that the disease is in most cases, over 90% is sporadic one and an age-related one. So I don't want to say that the data were not good, but they were overrated. There were no critics behind it.
I remember reading an interview from the 1990s saying, it will be scientifically extremely easy to look into this amyloid hypothesis, and we'll see right away if it's right or it's wrong. If it's wrong, we'll move on. That's 40 years ago. We are still having that same discussion. You were pointing out that it's hard for young people to do without the amyloid hypothesis if they wanted funding. But I think it was also very hard for established researchers. If you have made your life's work pursuing a particular theory, and you're then reviewing grant applications, and some little young person comes up and suggests that your work, for which you could become the blah professor at the fanciest university in the world, is all wrong, is it likely that you will see this sympathetically? And if you're human, it isn't a conspiracy, which I really love in your work. It's not that this is a cabal of people saying, let's do evil, we don't want to cure Alzheimer's, not at all. It's that the human, scientists are human. We think that we work only on evidence, but the evidence we put in front of us must be analyzed by human beings. And they have their own interests, they have their own blood.
Well, just to add on this, Nikos Romaki is sitting here helping me also with the book. He said, I think quoting you right, big egos have to be right. So, and that's the point you are making. If you're working for so long on a particular hypothesis, of course you believe that it has to be right. And but again, this is part of the story. And as a young researcher, when I was working, starting in Alzheimer's disease in the 90s, as described in the book, in the intro, of course I was flattered. I realized that I worked on a particular effect of the amyloid protein, and we had a great paper in a fantastic journal, and it got to work, and there was the CNN radio man, holding a microphone in your face, and of course, as a year of researcher, you were happy, you made something really great. Less critical then, you are starting to become spoiled a bit. Yes, but I think that's part of the story, that the big influencers have played a big role.
It is certainly not unique to the field of Alzheimer's research. This is an issue in science where people become very dug in on what they're doing. As you point out, one of the aspects of the book that I most enjoyed was your developing your own theory. I want to make sure I got the name right. Your sort of alternative
This matrix model, or call it matrix model.
Yeah. So I like that because the other cascade hypothesis, though it does explain some things, it doesn't explain some really important findings. It doesn't explain why there are people walking around all over the place in this room and elsewhere who have plenty of amyloid and are older and are fine, who live to 100 and have amyloid and don't have dementia. And the cascade hypothesis doesn't explain that. It's actually really, they try to bury it. Like, if they got older, they would get it. You know what? If you reach 100 and you don't have dementia, you win. Not we don't really need to wait for you to do any more of that. So I love that you break up Alzheimer's disease into different categories in your hypothesis. Can you explain that? I know you talked about it briefly, but how does that help in this problem?
It definitely makes things more and more complicated.
Okay.
And when you talk to, particularly to the big players in the pharmaceutical industry, they let you know that complicated things are hard to sell. People and investors like easy solutions. But I think it's a little bit too easy for a complex brain disorder. So, so the idea is that there might be patterns of genetic risk factors that are common to certain groups of people that determine the brain function and its adaptability over decades, over a lifetime. Then it depends, perhaps you develop a metabolic disorder or you have a brain trauma, injury, then your plasticity, your adaptability changes. If you don't have any risk genes, then you're fine. It's just you can cope with it and you go on. So this is sort of everything starts at the very beginning, determining how your brain will work out during aging. And yes, there comes amyloid also, as many of us have amyloid in their brain. But for some, it doesn't matter. For others that have more and more risk factors, it may matter. But so it's a complicated model which tries to integrate and to implement also the recent findings, the last 10 years of all these different genetic risk factors.
I think models in science have both risks and benefits. As in economics, if the economy isn't doing what the law proposes, obviously the economy must be wrong. So people fuss at that, but what I love about your model is that it embraces that this is clearly an incredibly complex disease. And we may not like it, we may want it to be more like a yo-yo, but it's not. It's an incredibly complicated machine. And I like it that you admit and embrace that. And it does a much better job, I think, of explaining or offering potential rules for amyloid. It's not that it's completely insignificant, it just doesn't have a role that we want to attribute.
I think in part it's already implemented, the model, but the idea behind it. Meaning, today patients are grouped in based on their ApoE genetic background, which gives you some risk factor already. And the ApoE story is really not funny, but it's interesting. Because ApoE4 as a risk factor was found in 1993, just about at the time when the amyloid was taking off. And this was a really important finding that ApoE4 allele variants, tenfold, 20-fold increase of the risk, but never really studied in detail. So if you ask around and do research and papers and talk to people, they say, well, it just came at the wrong time. Everyone was happy with this amyloid now as the culprit, as the big player, and so no one wanted to make things more complicated and focusing on ApoE as well. And then the people publishing ApoE finding data, they were not from the Alzheimer's field, they were metabolic researchers. So, there was also fighting of the camps. They didn't want to have intruders into their fields. And now, these days, AOE is really hot. It's really now the research we are seeing today should have been made 20 years ago.